okay? So heat capacity of solids, all right? So there's some gross looking equations on here, but hopefully you all might recognize some of this. So let's digest this, okay? So the heat capacity of all solids is given by the Einstein equation. So this E right here is E for Einstein, okay? We could also replace it with a D, and that would be for Debye. And you can see here the two competing equations of Einstein and Debye are very close. Debye actually got it right. So these values are measurements. And I'm not going to get into too much detail in the difference between the Einstein heat capacity of solids versus the Debye, because they're both very close. So we'll look at the Einstein equation. Okay, so what it says, it's the quantity 3 times R times this function of T. Okay? So let's talk about why 3R. So if I have a solid, okay, in some lattice, right? And I'll just put like one little, atom or something like that. Suppose we're just talking about something really simple like silver or lead or iron or something, okay? Well, we know in the solid, it's not going to be free to translate. It's not going to be free to rotate. It can very subtly vibrate against the other lattices, okay? It's very subtle. It's a very, very low energy vibration. If you recall from your FTIR days in CHEM, those solid vibrations will appear way down in the fingerprint, like 500 wave number and below. And as it turns out, that makes them low enough in energy to matter for equal partition. And in a gas, whereas we said there's 3 degrees of this translational freedom, right? It can move X, Y, Z. Well, the solid, when we think about the solid kind of vibrating against its other, neighbors, that is kind of like a translation in some ways. It's trying to move, right? Let's say it's trying to move out in this direction. But of course, as soon as it moves in that direction, it's going to hit, it's going to be really close to another neighbor. So it's going to want to influence it to go back the other way. Okay, so that's what's going to give it that vibration. Similarly, it would happen in this coordinate, and it would also happen in this coordinate. So how many degrees of freedom does that represent? If you said 3, you're not thinking 3-dimensionally. Because remember, in a gas, the next nearest neighbor is way far away, like down the street 10 million miles away, practically, right? So whether a gas moves in the positive X or positive Y, or positive X, negative X, positive Z, negative Z, whatever, right? Those are degenerate. They are not for a solid, because a solid has neighbors, okay? So we get 1/2 RT for each and every one of these motions. Okay? So the positive X and the negative X are no longer degenerate in a solid. So that's 1, 2, 3, 4, 5, 6 degrees of freedom, 6 1/2 RTs gives me 3 RT. And remember, partial of U by partial of T equals the heat capacity, which is 3R. Okay, so now, in the heat capacity of solids, CDM equals 3R times this function. So that's where the 3R comes from. But what is this function? Well, I hope you've been staring at this long enough to think it's a partition function. Right? Let's look at this. E equals theta E divided by 2T, where theta E is h nu over kb. Let's plug that in, okay? So E raised to the power, so that's exponential, raised to the power theta divided by 2t. That's going to be e raised to the power h nu, and look, divided by 2t, that's going to be 2k Boltzmann t. Oh my God, that's it. That is a partition equation. And what does this theta e represent? That is what we call the Einstein temperature. Okay? And as it turns out, the Einstein temperature, so if you look at my scale here, so this is again another reduced variable space scale. So this number 1, when this is 1, that means the temperature equals the Einstein temperature. Okay? And so I'll give you an example, because I know it off the top of my head. For lead, the Einstein temperature is roughly about 105 Kelvin. Okay? And so we would get that by saying H times, so this is the frequency of vibration. Okay, so that is, so look, H nu, right, gives me energy. Okay, E equals H nu, right? Don't forget that. Okay, and so this is all energy divided by K Boltzmann T. So that's the frequency, I'll just say freq of vibration. So, and that's in hertz. That's in units of 1 over seconds, because my Planck's constant, right, is joule seconds, okay? So, those vibrations, it's going to be something like, 10 to the 12 hertz or something like that, corresponding to about 500 wave number, the fingerprint region. So if we go and calculate that, each solid has its own Einstein temperature because its vibration and its lattice is unique. So for lead, this would occur around about 105 Kelvin. And if I follow this up here, look at this, okay? This scale is CV divided by R. So, right, that's 1R, 2R. So here's, I'll put in parentheses, 3R is the top of this line. And look, the Einstein temperature is this temperature at which the solid approaches its bulk classical heat capacity. All right? So in other words, at 298 K, this equation just becomes 3R. Because at 298 K, this partition function no longer matters. That partition function approaches the value of 1. Okay, so in other words, above the Einstein temperature, there's sufficient population of states that all of those vibrations can be accessed and populated, okay? And thus our heat capacity will exhibit its bulk characteristic heat capacity, which is 3R for all solids. And you might be thinking, how the hell is the heat capacity 3R for all solids? Well, check out how this works, okay? Look, it's 3 times 8.314 joule per mole K, which equals, the quick calculation, I meant to have a calculator out in front of me for this lecture. So 3 times 8.314 gives me, I'm just going to write about 25 joule per mole K. So how is it that all solids have the same heat capacity? Well, remember, it's the specific heat capacity, the joule per gram per Kelvin, that gives us that unique value, okay? And so, for example, if I want to calculate the specific heat of lead, let me look up the molar mass now, of lead is 207 gram per mole. So I'm sorry, this is getting a little sloppy here. So now I know in 1 mole of lead, it's 207 grams, okay? So the specific heat of lead is about 0.12 joule per gram per Kelvin, okay? Which would be different than the specific heat of iron or of manganese or whatever, right? So the heat capacity of all solids is 3R, once you're above the Einstein temperature. However, you have to remember the specific heat is different. And I'm going to do another cool example